So good morning to the people that already signed in. Good morning, everyone. So this is the tutorial number 4 on doing spectroscopy data analysis and calculation in the Jupyter notebook. I'm Marius Retegan. I'm part of the algorithm and scientific data analysis group here at ESRF. And we will be together for the next 3 hours. You do as you want, but since we are in a rather limited number of people here, if you don't mind, you can also start your camera so we have more of an interactive discussion. And yeah, I would also have to get feedback from you, because otherwise I do not know if the things I'm saying make sense or not. The outline. So what I intend to present to you today is outlined here. I'll start with a brief introduction on Jupyter Notebook and an overview of the data of the tools that are available to analyze the experimental data. Then we'll do some practical exercises on data reduction and analysis. We'll take a coffee break, and finally, it's going to be the second session is going to be a bit longer on theoretical calculation of X-ray spectra, and this is going to also be having a short introduction to the theory of these calculations, and then we'll go to do some calculation in the Jupyter notebook. Now there is this in these 3 hours of excluding 2 hours 45, excluding the coffee break. There's quite a bit of information that is packed in. First of all, it's the fact that all is going to be done in a Jupyter notebook. I hope most of you are at least familiar with the platform. It's also going to be done in Python. So there's not going to be a lot of user interfaces. Everything is going to be done via code. And there are 2 aspects. There is the experimental part, which is to know how these type of experiments are being performed. So in the practical session, we're going to talk about this. So you have to know a little bit what such experiment involves. And the theoretical calculation, it's another let's say difficulty, because it presents, there are some theoretical notions, so it might also be very difficult for some of them to be answered. I try to keep it simple, but just so you know, there are quite a few aspects of this tutorial that make it maybe a little bit difficult. So I'd like to start by presenting you, telling you a little bit by what Jupyter is. So there is a big project, Project Jupyter, which develops and supports several interactive computing products. You have the notebook. It's the thing that we're going to use today. But then they develop some other stuff like Jupyter Lab, which is more like an IDE in your web browser, or the Jupyter Hub is the thing that you are connecting to access computing resources. And this is what we're going to do today. Voila, which turns these Jupyter notebooks in standalone web pages or web applications, so that you can use without connecting first the Jupyter Hub. So you can find information about this on the official website, which is jupyter.org, or if you go on Wikipedia. So the Jupyter notebook, it's a web application. Okay. So someone joined the wrong tutorial. So Jupyter Notebook is a web application that allows to create and share computational documents. And here is an example of such a notebook where you can have here a combination of explanatory text, mathematic equations, but you can also write Python code, which in this case allows you to change the parameters of this function in order to change and to replot the function with every parameter change. So this is what we're going to use today. And to do this we're going to use the ESRF resources. So I would like you all to go to this website. It's enough to just type jupyter./slurm.esrf.fr, and maybe I can put. I will put in the chat and also I can share the slides if you're. So this is the website, and then I can also put a link to the slide, and here are the slides in case you want to have a look at them. So did you manage to connect to the web page, or like to have it available? So as I said, I would. Yeah, Andreas, yes.
Yeah, I have connected, but it says server options now.
Yeah, exactly. So yeah, that's the first step. So just if people manage to yeah, exactly. This is my. So I'm just going to log in, and the other people. So I'm just going to call by your first name, Natasha, Dimitri. Did you manage?
Works for me.
Works for you?
Yes.
Yeah. Hello.
Yeah, I've managed.
Okay. So. Yeah. Okay. So I automatically connected because. Let's see if I manage not to connect. I'm just going to log out. So I'm not. Oh, sorry. I'm just going to log out because I have to show you exactly the same page and how to. So control panel and just stop server. Okay, so start my server. Okay, launch server. So you should be here, right? Is that correct? I mean,
Yes.
I think we're not many of us,
yes.
so you can. I mean, if it's you don't have background noise, you can just unmute yourself if it doesn't matter. Then we go to you should go to advanced. Change the number of CPUs here to 2, and the job duration is for 12 hours. It's a bit more than we need. And then just type in the reservation field tutorial 4. And this is a reservation that was set up in advance, and this allows us to automatically connect to the resources. Okay, so then after this, you're going to get this page. Do you have experience with Jupyter Notebook or not at all? I mean, you ever used it? And
Not too much. I've looked at it, but I have never used it.
Okay.
I also have.
Yeah, go ahead. Sorry. Okay, so in the end, many people talking at the same time is not that. Okay, so not that much. So okay, so
sorry, it doesn't show what you show. It says unknown status.
Unknown status. Okay, so I'll just I'll stop my server. Let me redo this again. Start my server. Okay, so you go simple, advanced, and you do.
Now it comes. Now it comes.
It comes, right?
Now it says your server starting up.
Okay.
Yeah. For me, It also says your server is starting up on the top, but then later spawn failed in the red bar. Is it
Okay.
how it should
Exactly
be?
the same.
I need to check. Shouldn't have this. There aren't that there aren't that many people that are using the cluster, so in principle it should not be a problem. Just can you try again? And maybe I don't know. Maybe okay. Let's reduce the number of hours to 10 because they have some for people who did not manage to connect, of course. So
Now worked with 10 hours.
with 10 hours it worked.
Yes, for me.
Okay. Yeah. Karolina, could you please try again with 10 hours? Maybe that's. Maybe
Yes,
that's
now it worked.
it works. Okay.
Yeah.
Excellent. Okay, so it's what I said here. Go to Advanced tab, CPU, job duration 4 hour, and tutorial tab, and then you press start. Okay, so now we have resources in order to use like some of these libraries that we're going to use today for data analysis. You have to do the following. Go to here to new, and then terminal. It should open a new tab. And then I'm going to copy, sorry. I'm going to copy the command you need to run. So just copy from so the command is also in the slides, but you should copy it from also in the chat. So this is a bit, I hope this works. So I'm just going to do the same thing. So what I said. So in this terminal, you just type, I can explain to you why modulo. Okay. So you should see the thing change to something like this.
Mm-hmm.
Yeah.
Yep.
Excellent. And then you just type. I'm going to put the command again. Kernel install. Kernel install. So a bit of like I want to explain what exactly is happening. In order to, as I said, in order to use some of the libraries that are developed for spectroscopy data analysis, at the ESRF, we said, sorry?
So it says kernel install, it gets one page of error messages.
It's kernel install. You get an error?
Well, let me see if I wrote it right.
I'm getting error 28, no space left
Exactly.
on device.
Yeah, exactly. I get a lot of lines on top, and then it says error number 28, no space left on device.
Yeah, we had some issue with it's not related to this tutorial, it's not related to.
Okay.
We had some issue on Friday. We were actually thinking whether or not this is going to happen on Monday. So I think it happens for some, but some of you managed didn't get any error. Everybody got an error. Did someone didn't get an error? No? Okay.
Seems everybody got it.
Everybody got it. Okay. That's not a very good news. Okay. Could you please pass the error in the chat? So I just, in principle, I mean, there's nothing that I can do on my side because this is related to the computing services here at the ESRF. So, thank you. So, okay.
There's
So
a lot of text on top, huh? So it says a lot of text on top. It says that you wanna
trace back.
Trace back.
exactly. Yeah.
Yeah, that's Python related, but in what it says in principle is that it's not able to write files on disk.
Yeah.
So, which is very weird because it should not be the case. Okay. Okay, so let's. I mean, it's absolutely nothing I can do about this because it's a competing service. I can contact them in the break. What I suggest to do, because this session is also recorded, I will. Excuse me. I will just go ahead with the presentation, show the step that usually you should have done, and then you could replay it again. You'll see me do most of the things, and then you can focus on what I'm doing. So it's going to even be easier for you to follow along than just to switch between my presentation and some possible errors that you might get. This is not very easy to do. It's already very complicated to do in person because errors like this can happen. But I think via Zoom it's even more complicated. So let me go back to what I was trying to say. So this sets up an environment that contains all the packages that can be used, or like most of the common packages that are used for data analysis for spectroscopy. Some of you might know Large, maybe. That is used for X-ray absorption or ZAFS data analysis. And NumPy, SciPy, and stuff like this that might be useful for you. And with this command, kernel install, you make this environment, which is a Conda environment, available in the Jupyter notebook. So here, after I run these commands, I could go back and do a new, and then I do a Python 3. I would have this Python 3 spectroscopy. So you would start a new notebook. Okay, so this is described in the presentation, what you should do. Now, as I said, a Jupyter notebook can contain source code, like Python code here, or Markdown text, which is a way to write, rapidly write, quickly write text that is, for example, contains titles and even mathematical equations. So let me just say, so by default you get code. So if you type, for example, A is equal to 1, and then you type Shift Enter. Okay, so now I'm starting to get errors. B is equal to A plus 1, and then I type run, for example. You can run, and then you say what is B. B is equal to 2, right? So you can write code, okay, simple code, and then, for example, in here I have A is equal to -1, and it says if is smaller than 0, then print A is a negative number. Otherwise, print A is a positive number. And in this case, because A is -1, is going to print A is a negative number. I think Python as itself as a programming language is relatively simple, and this notebook interface allows for user to more easily experiment with it. So then you can also type mathematical equations. But in this case, so by default, as I said, this cell is considered as code. But you can go to cell, and then you send cell type, and you say markdown. Now, if I type, this is markdown. This is just a name like LaTeX. It's just so this is markdown. You see, you don't get any reply, and then you say math using dollar. So, for example, alpha. So, okay. Okay, so it's I think for this Jupyter notebook way of writing code, as I say, I think it has eased a lot the way people has changed a lot the way people perceive Python, because in this it's easier to experiment and just easier to write simple snippets of code and just to see what the result of that code is. So it's less intimidating. So this is what we're going to use all day. These are I prepared some notebooks which are for the data analysis part and for the computational part. And before we go into this, I just want to tell you a little bit about the ESRF and what changed for like a year now, is that ESRF has had the EBS upgrade. And with this EBS upgrade, they introduced a new control system. Before, everything was based on Bliss. So I assume most of you did experiments at the ESRF, right? Or like, so you have some idea about experiments in general. Like before, used to have this.
Yeah, sure.
Yes.
Okay, so before you used to have this control system. So this is being replaced with Bliss. Bliss is a tool that is it's more advanced control system. It's written in Python. With this, ESRF also changed the storage format for all the files resulting from experiments to HDF5. Now, most of you did. I assume because you're here, most of you did spectroscopy experiments, and in these experiments, you know that even the spec files were ASCII files. So if you would open them with a textbook, with a notebook, sorry, with the text editor, you could see exactly what's inside them. With HDF5 file, these are binary files. So if you try to open with something like Notepad, let's say on Windows, it's just you do not understand anything inside it. So to actually visualize these files, you have to open with dedicated visualization software, and PyMCA, which some of you might know, it's able to use this to open this HDF5 file. Now, what's an added thing that was introduced to these HDF5 files is the Nexus format, which is actually an HDF5 file with additional rules on top of it. So add some structure, like what is the instrument, so like metadata about the instrument that you use, the sample that you use, and so on and so forth. So this is just like for you to know some history about what changed with the new control system and file format. Excuse me. So when you go data analysis for spectroscopy, the data reduction part is actually not very, let's say, not very complicated, because it involves steps like spectral averaging, rebinning. Sometimes you do background subtraction, quick fitting, and the plotting, and then you put the spectrum in the publication. What is most, let's say, time consuming is interpreting these results. And this has mostly to do with assignment of spectral features and trying to extract some information from the spectra, like oxidation states, structural parameters, and crystal field parameters. And this is done by comparison with spectra, reference to the spectra, reference compounds, but it can also be done with theoretical calculations. Now, with what concerns the data to analyze this, the spectra, like the tools to analyze the spectra, you have a series of tools that I hope some of you have heard about. These are the Demeter suite tools. And there is also a tutorial this afternoon that is introducing them. You have large. You have large, which is it's supposed to be an it's supposed to replace the Demeter suite in the future. This is developed by Matt Newell. And of course, you have something like YMCA, which I think most of you are familiar, which allows you to visualize the data during an experiment and to plot certain, like the spectra that you are measuring. One aspect about data analysis done using these tools is that they focus a lot on X-ray absorption spectroscopy and EXAFS, and not so much on other type of spectroscopy like X-ray emission or RIXS. And here are the beamlines that where you can do spectroscopy at ESRF. And as you can see, yes, most of them do X-ray absorption, but there is an increasing number of beamlines that do X-ray emission and RIXS. And there are not that many dedicated tools to do data analysis for this type of experiments. So to achieve this, or like to get started with this type of analysis, even though it's not complicated, we have developed here at the ESRF a tool, which is data analysis for X-ray spectroscopy, which is an acronym for DAX, which is a acronym for data analysis for X-ray spectroscopy. And this is what I'm going to show you today, how you can use this Python library to do data analysis for simple experiments, X-ray absorption, emission, and RIXS. Okay, so yeah, if you wouldn't have had problems with space on device, this is the things that you would have had to do. You would have cloned another repository, so you would have copied from a server a repository that contains all the notebooks, and afterwards so afterwards, if I go back here, after you would have done the clone, you would have had this. Let me just. So you would have had this folder in your home folder, and in it, the notebooks that we're going to use today. So the first one is the X-ray absorption. This is very interactive, so if you have any question, please don't hesitate. And everybody says that, but really, it doesn't really work, because otherwise I'm just talking and it feels a little bit long. So if you have any questions, please interrupt me.
I have one very general one. Now you
Yes.
showed everything installed on the server of the ESRF. How we get this on our own computer?
I can provide notes. I don't have it in this presentation.
Because at the end of the day, it's intended that we get this that we analyze data finally on our own computers. I guess not on the ESRF server.
Yeah, but okay. Yeah, I understand your point, and I can certainly after this tutorial is finished, I can send you like the steps you have to follow to install this locally.
Thank you.
The only so this ESRF made this Jupyter Slurm available to the users to avoid this type of requirements, because maybe for the spectroscopy it's not such a big deal because the amount of data is usually very small, so it's no issue in transferring the data. But there are other type of experiments where they have large, like terabytes of data, which are very difficult to download. So you do the processing on the ESRF servers, and then you can download it locally.
Okay, so the idea is actually that we run it on the ESRF server.
Yes, so it's easier. So it's easier for you because you don't have the issues with installing this type of software locally.
But we have the issue that it doesn't work at all.
Yeah, that can be solved. In principle, it shouldn't be an issue. But I don't know what's happening. It's something related to the networking files server NFS that didn't work on Friday, and we are crossing our fingers that it will work on Monday. But apparently, it doesn't work for everybody. So yeah, that's an unfortunate event for sure.
Okay,
sorry.
Sorry to interrupt you.
No, but I understand it can be frustrating when things don't go as expected. Okay, so X-ray absorption spectroscopy, and okay, sorry, just so to go back a little bit to what you were saying before. When you come, for example, to the beamlines and you measure on, let's say, on ID26, because that's the beamline that has this new controlling system and uses these libraries. The local contact will usually help you have some starting, let's say, like a starting script to analyze your data if you're not familiar with it. I mean, you can do it however you want. You can use PyMCA, export spectra to text file, and then do the analysis in origin. But that takes time and it's not very reproducible. But if you come to the beamline, the idea is that the local contact will also give you some help. It also help you to do the like a simple script or a simple notebook to analyze your data. Then when you go home, it would be easier to redo this on the ESRF server. But as I said, we can send you notes about it. Okay, so X-ray absorption spectroscopy. So in this notebook is going to be, I'm going to present to you how to reduce X-ray absorption data. If you are, I hope you're all familiar with this type of experiment. The idea is to use X-rays to excite a core electron to the unoccupied orbitals, and depending on where this electron, let's say, will settle, you would get a pre-edge feature. In the case, for as it is represented here, if you do a 1s to 3D transition, you would get the pre-edge features which are represented in green. If you go to 4p orbitals, then you would reach the edge, and then everything above it would go into the continuum, so you would have the XFs region. So what you need to do is to, in order to analyze the data, the first thing is also, of course, to look at the data using a visualization program. So I'm just going to open the file, and then I'm going to show you the PyMCA so just, so the experimental data that I'm going to use, it's in the folder experimental data, and this is an in-house experiment, and the file name is this one. So I'm just going to open that file. Okay, so let's see. Okay, so let's see, and then I'm just going to okay. So this is how the data looks when you load it in PyMCA. There are a number of scans that have been measured for this chromium oxide. So these are not scan number 4. Let me see if I can go back. So number 4 to 23. And the x-axis is this HDH energy, and the signal is the detector DTC. So this is information that is provided to you by the local contact. So usually this is the type of information that that you have when you're doing the experiment. The monitor is it's another value that is used to divide the signal. So you have the x-axis, which is the HDH energy, the signal, which is that DTCAPD, and then you divide the intensity of this signal by the I02. And this is what you get for as an X-ray absorption spectrum. You have here the pre-edge region, the edge, and then you have the excess region, which extends to a certain energy. Now, there are a number of scans, so there are, this is of course done to improve statistics. So if I would just select scan number 7, 8, and so on and so forth. And, so these are all measurements done on the same sample in order to improve statistics. So there is some information that you have to provide to the script. First is the file name that you want to process, and the scan IDs. And then you say, I want to process the scans from 4 to 23. And with this information, you define a source of scans, if you want. So you say source, which is something that you execute in this first cell. When you say here, what you're doing is you're importing the required libraries in order to do this type of information, to do this type of processing. So you have NumPy, which is a tool for array processing, and then you have the Matplotlib library, which you can use for plotting, and then this data analysis for X-ray spectroscopy. You have a source and the type of experiment that you're going to process, which is an X-ray absorption. So I'm executing this. It takes some time to execute, and then you can even look at what you're having on disk by running exclamation point, and then you run commands that you usually do on a Linux system. So you run exclamation point ls, and then you experiment the data. So you can also click on run. And you see I have a number of folders where I have in-house experiments done on Beamlines. This is data that I can show you. And okay, so you first, okay, as I said, you first define a source of these scans, and then you define the counters that tell to this library what is going to be the x, how is going to take the x value. The x value is going to be the HDH energy. The signal is going to be this, and the monitor is going to be I02. Okay, and after that. So there, after that, you define the measurement. You know that this is an X-ray absorption. So you define a source of scans and the counters. So you write here the source of scan and the counters. You execute it. So let me execute it again. You can use Shift Enter, or you can press Run. And then once you have done this, it's possible to just do measurement.x, and this is going to give you, let me just show you, so I'm going to set below. So, sorry, measurement.x, and this is going to give you what is the x value common to all these scans from 4 to 23, because it must be said that specifically when we do this type of scans on ID 26, the range of energies is not always precisely the same. So it might be that one scan starts like a very few 0.1 EVs differently than the other, or that the number of points is not exactly the same between them. These are what are called fast scans, so they are not identically mounted. So when you type measurement.x, what happens is that the library is going to compute a common x-axis with a minimum and a maximum and a step for this, and is going to give you also a number of points, which in this case is 615. So this is the number of points in one scan. And what I did here when I typed measurement.x, I just asked to plot what are the values of those 615 points. So you see that. So here are the values on the x-axis. I can also plot. I can also ask for what are the values for the signal, and you have an array of 615 points. Okay. So now that I have this information, I can just simply plot it. Let me just guide you through what happens here. These are matplotlib related instructions. I'm just saying that I want a figure and an axis, and this is the command that I'm using for that, plt subplots. Plt is something that you matplotlib pyplot is imported here. And then I say, on this axis, please plot the measurement x and the measurements signal. And then you set some information like the label on of the x-axis, and then the label on the y-axis. Okay, and then you do you plot this. Okay, so I'm also getting errors. I think is related to the same errors that you're getting. But for the moment, it works for me, so it's fine. So this is a plot of the aggregated scans, meaning that it takes all those 19 scans together and does an average. That does an average of them, and this is the result. Now. This is a lot of information. If you have any questions here, I would be very happy to answer them. So please don't hesitate. All good? Okay. So I will continue. So the question is how we aggregate these multiple scans. There are two ways of like that. You can think of two ways of aggregating. You sum first the signal of each of the scans, 19 scans together, and then you divide by the sum of the monitor signals. So as it says here, this might not correct for instabilities in the monitor signal, but there is also an alternative to this. You do a sum of fractions where each individual signal is divided by the monitor, and then it's added to the final intensity signal. And this may not give a correct statistical weight between scans, and you can also lose the total counts. So I want to present these two ways of aggregating your data. By default, the library is going to do a aggregation using fraction of sums. So it's going to use this type of aggregation. But we can reset the measurement, so you do a measurement reset, and then we can aggregate using sum of fractions, which is the second way, and then plot the result of this aggregation. And when we call give me measurement, the x value of the measurement, then the x is not going to change, of course, between them, but the signal is going to change. So this is the result. You see the fraction of sum in blue and the sum of fraction. Of course, because they have different ways to do the summation, the intensity of the two aggregated signals is not the same. So what we can do is do a normalization, and we can normalize the reduced data, and we go to the same process as before. But now, when we do an aggregation, we say aggregation fraction of sum, and we also specify that we want to normalize to the maximum. And we do the plot, and let's see how. So you see that now the both spectra are normalized to the maximum. So the highest intensity is 1. And this is the spectrum. The spectra almost overlap, so visually they overlap, but if you were to zoom in, you would see that there can be some differences. To what extent these differences are important depends. It might be actually that these two ways of aggregating the signals might give larger difference than this one. But we also see the way it is plotted here that most of these differences come in the post-edge region, maybe a little bit in the pre-edge, but they are larger in the post-edge. Also, the relative differences between the two is not really that big, so it's excuse me. Sorry. Okay, so you see that the differences is not really that big, but like it's relative to this is actually relatively tested. The signal is it's actually very small. So, in conclusion, processing this data, X-ray absorption is not very difficult, like to do this type of summations or this type of aggregation. But if you were to do it outside using something like even PyMCA or even exporting the data and then doing this type of processing in origin might be more complicated. The idea of developing this type of libraries is to provide a relatively simple way to do this in Python. And also the advantage of doing this in a notebook is that once you close this notebook, so you save it and you open it, let's say a few months from now, and you want to look at the data, is that you're going to have the plots that you made and everything that is resulting from your analysis are still going to be there. So you're going to have basically something that is going to be reproducible. And even, as I said, in 2 months from now, you're going to be able to see exactly what type of analysis you apply to your spectra in order to get the final plot that you put in a publication.
Excuse me, I always had this difficulty with this notebook. So now I see that you save it like you do, but now we are running, I don't know, 100 scans in one trip. So we'll have 100 spectra. So how would you do when you measure 100 different spectra? You write 100 notebooks, or what is the idea?
No. So the way you can think of it, you can run multiple in the notebook. You're not limited by how many data analysis you do. But for example, the way I organize it is that, let's say, for when you are measuring an X-ray absorption of an element and you want to have a processed spectra of that element, you just do a notebook, let's say, for that experiment, for that measurement, and you don't. So you write a simple notebook for an experiment. Of course, you could process multiple files in the same notebook. So I could just, let's say, I could just copy this. Let's see what, because I didn't check this. So let's see if now I know that there is also a file which is called 01 and 01. So this is another file that was created during the experiment. I'm not sure about the range of scans. So let's, for example, I could look, let's say maybe, okay, 4 to 10. And then I do the same thing as I did before. Okay, so now there is a problem because, okay, so this particular file doesn't have the same, that doesn't have the scan. So that's why it's very important to look at the scans initially. So you have to look this with a program like PyMCA or something like that. You have to,
but now let's say you do experiments and you would like to analyze them, and you have about 100 scans. So what you're suggesting is that you write a notebook for every scan you copy in this, and you do this finally 100 times in an infinitely long work.
No. You write a notebook. I mean, here you change the number of scans to whatever,
Okay.
So whatever range you want.
Okay, so I'm changing the notebook essentially. And
You change, yeah, you change the notebook. I mean,
okay.
they are. I know that they sometimes measure scans that they have to do very fast X-ray absorption. They have poor statistics, and sometimes they measure like 1,000 scans.
Mm-hmm.
So in that case, you just change the range here, and the scans. These scans are going to be read from the file, and then they're going to be processed. And that's it. So.
I make about maybe, let's say, a couple of scans on each sample, but then we're measuring 20 different samples in the end of the day, or different states of the samples. I do some chemistry, and then obviously I get 10 sets of experiments in, let's say, in 10 hours or whatever.
Yes.
So then I would like to analyze finally
all the
hundreds
data
of different samples. Yeah. Not
okay.
Scans, essentially, not summarizing the scans because they are all changing. So I have a reduced sample, an oxidized sample, a sample in contact with something. So we'll end up having many, many data sets, and how we analyze these many, many data sets.
So let me show you what I would do. So you would have file names. So let's say file 1, so file 2, and then whatever. So let's say you have these two files, and then scan IDs, and then you would have for each of these files, you would have let's say 4 to 12, and then 5 to whatever 45, 35. Okay. So assuming that all of these are X-ray absorption scans, you would do something like that's the power of doing this programmatically, because you can use control loops in Python exactly for this purpose, like to process a large amount of data that usually with an interface is more difficult to do. So I would do for scan, scan IDs. So let's say IDs, and then I would do something like this. It's a bit, so there is a very, I would say, maybe from my perspective is not the best perspective, but I would say that yes, there is a bit of a learning curve that one needs to adapt to. But I think once they are presented with an example of how to do things, even if it's done programmatically, they can adapt to their use case. So I can do file names, scan IDs, and then I would just do so a source for each file. So I would have source file name, and then IDs, and then measurement. Sorry, it's EXAS, and then a source, and then the counters. So the counters, assuming again they are the same.
You've written measurement wrong, but.
Okay, so and then you could just after you do this analysis, you can just say plot all of the resulting. So whatever, so PLT, it's actually an axis plot. So is this answering a little bit your question?
Yeah, but the syntax is, let's say, very difficult to.
Yes, I know, but yes, I agree that
if you're used to work with it, but if you just come once and try to do that, and then you have to remember all these loops and everything.
But
that's
think it
complex.
of it. Yes, think of it from this perspective. I think you're absolutely correct about this, and usually this is why people request most of the time graphical user interfaces, because they are simpler. But I believe that if these type of notebooks, like I'm presenting to you today, are sufficiently large number, so people can learn by example, can adapt for something that works, they can adapt it to their use case. So it's if I would give this to someone, and then I would say, okay, this is a notebook to analyze your X-ray X-ray absorption data experiment that you did. You have to change here. You have to, of course, change the scan IDs. And then even have something like you requested, something that can analyze more scans at the same time. So ignore the. Then I think it's easier to adapt to the use case, and you gain a lot in terms of how quickly you can analyze all this data. I agree with you because it's a bit complicated, but I think there is a lot to be gained by using this type of approach to analyze data. As I said, my perspective is not the best, but
let's see. This is the reason why I'm just watching this this presentation to see.
Okay.
How to do that?
Yes.
How to learn how to do that?
Yes. There are two aspects here that might create some difficulty. First, you do not know the data that I'm presenting to you, so you're not familiar with where the scans
the data
are.
looks pretty much like we also collecting.
Okay.
It's more the way of
okay.
We measure not chrome images, but we measure a lot of other edges.
Okay. I think here, going forward, is going to be like when you're going to be on a beamline, I think the local contact is going to provide help to get you started. I mean, depending on the beamline, I do not know on what beamline you measure. So
measure 9026.
Okay, so then the local contact, when you're going to do the next experiment, the local contact will going to I think help you with setting up this type of analysis. So yeah, that's, as I said, there is a lot of power because you can use this type of for loops. You can go quickly over a very, very large number of samples. In principle, here I could have, I don't know, you can have 20 or 30. I did analysis like this for 20 samples, and you just enter the file name, the scans that you want to process for each file name, and then you do the analysis, and that's it.
Okay, maybe I misunderstand the whole situation. So I was thinking that we're going to learn how to analyze data in general, but what you're saying now is how to analyze data measured just at the beam time. Because of course, then you have old data and data measured at other places, and you would like to compare that and use the same, let's say, the same software.
Yes.
It's not too good to analyze data from, I don't know, from Hamburg with I don't know, with Athena, and to analyze data from Grenoble with your program. It's
yes.
But the idea is actually this is just to analyze the data when you are there doing the experiments. This is not what I understand, or.
Yes, but okay, this type of programs, like this type of libraries, can be used everywhere as long as the data, as long as the data has the proper format. So I do not know what exactly it's used at Hamburg, for example. If they are still using spec files or it's switched to
ASCII files, similar to spec. Yeah,
exactly. So that's one of the issues in trying to analyze data from multiple places, because nobody can agree on what the format is for everybody. So at ESRF we're using HDF5, of course we use spec before, at some place they use something else. So that's the most difficult, I would say, part, because once if you would have like a something that resembles like a common format, then all this data analysis can be repeated with data from any type of beamline and facility.
But maybe I comment to Andreas. So as long as you can import an ASCII file and you can import it, basically you need two columns, energy and intensity. And when you do the same exactly.
Yes.
So Marius, we are able to import local data from our computers, I assume.
Yeah, it's not so like ASCII files, for example.
Yes.
Yes, it's possible. That's let's say, a little bit under testing because it varies a lot. If it's only 2 columns, like and maybe a third column with a signal, yes, it shouldn't be very difficult. But this is mostly geared towards analyzing the HDF5 file because these are binary files, and people in general, scientists, when they come to the beamline, they see this format that they are not able to open with a text editor, can be very intimidating. So that's the whole idea of the whole concept of developing a library that helps with reading the files and doing the processing.
Yeah, no, I had a little bit different question. Are we able to import basically from local computers to the Jupyter hub on ESRF? Because the data you are showing is based at ESRF servers.
Correct.
We import what we have.
So in principle, to transfer data from your local computer to the ESRF.
Yes.
Yes, it is possible, but depends on how let's say used you are with let's say with using something like SSH to connect to the server.
Okay.
There is just maybe I can show you a little bit. So with the same thing that with the same login, you can connect to this remote ESRF.fr, and then you can do a remote connection to a desktop. Okay.
Mm-hmm.
So okay, and you can. The advantage of this is you can also use something like PyMCA to visualize the data. So even if you're remote at home, you can do this.
That's the instance which we just started for this tutorial, right? You connected.
It's different. This one is remote.esrf.fr.
Yes.
This allows you to see a desktop on ESRF computers. When we started the tutorial, we went to Jupyter Slurm.
Yes, but we basically started with virtual machine to which you have connected now.
If you started, sorry, I didn't.
So normally, if I go on remote.esrf.fr, that's related to the experiment or proposal. Basically, previously I did it to connect to the beamline control computer.
Okay.
But now you have connected to some other machine, which is what we started on Jupyter Slurm.
Yes. So
okay.
I can.
Yes.
So, so this is my local computer here.
Mm-hmm.
Okay, so let me answer your question. When you connect to a remote.esrf.fr, you are connecting to a machine that is a front end for the computing cluster. When you connect to Jupyter slurm.esrf.fr, you are connecting directly to a computing node. So you're getting resources which are dedicated for you. You get 2 CPUs which are dedicated for you, and you can do your analysis. What you see here right now is I'm connected to a front end where it's just for you to visualize the data and so on and so forth. So for example, if I do an ls, oh, sorry, I cannot make it larger, but we have data.id26 if you're measuring the ID26, and you have so you have all your data which is here. So you can look at it. Now you asked me about transferring data from your local computer to the ESRF, right?
Yes.
Okay. So let me show you an example. I have here the notebooks that I'm presenting to you, but which are locally on my computer. Okay, and then I do an SCP, and then I copy this, let's say this example, this notebook, to something that is firewall.esrf.fr. I can think of a better way to do this later, but for the moment, this is the only one that comes to mind. So it's a rather, let's say, long command. So I'm not that used to. I'm not actually that used to copy files from.
Okay.
Okay. So this is working. So sorry. Okay. So SCP, you have to specify this port and the file, and then where you want to copy it. And if I look here, I should see. Yeah.
And maybe explain why the question, because, for example, if we want to use a reference data which we have for years, maybe.
Yes. Yeah, this is the way to copy it, or I mean, there are also, if you're, I assume you're on Windows, you have something like I'm not on Windows, so I cannot really show you, but like something like WinSCP, which allows you to so the graphical user interface, and I don't have any.
Okay, but that's all fine. But I don't think for us it's the best way to. But my personal opinion, I don't know how Dimitri says about it. But I would prefer to copy files from the ESRF to my own computer, because I will have a lot of data I would like to compare it. Because I have not only a single file which I would like to compare it, but we have many files from old experiments, from other beamlines. And if I now copy all this data to the ESRF, I think it will be.
No, we will not get that resources at ESRF.
Exactly. It's not a problem of resources. It's not very comfortable that we copy now all our data towards the ESRF and then analyze it there. So the idea is obviously to copy the data from the ESRF to our own computer. No.
Yeah. And Andreas, basically, I think it's. Well, one can, Jupyter Notebook is open source and free, so one can set up an instance at the home laboratory.
Yeah, I know.
I think
all those codes we can do at home.
So what I can do after this tutorial, as I said, is to provide detailed installation notes for how you can do this locally for you. So this way you will be able to install it locally for yourself. So,
but there's still the issue with having to read in the program, the data format, because as Dimitri says, usually we have ASCII files.
Then I
not even 2 column or 3 column format, but we have this multi-column format from Hamburg or whatever, where we have to decide first where's the counter and where's the monitor and where's the energy.
But these are decisions that you have to make in any case, correct?
Yes.
Okay, so then the issue is how you can import that data, which is from various sources, into
the notebook,
into a library like this one. This has to do a way to solve this problem is to like for me, which I wrote the analysis part of the analysis library, is for you to send me, if you're willing to do so, a file that you want to process with it, and then I can adapt the library in a way that can process that type of file. You know that that's the whole complication of not having standardized way to store data on disk, is that every new library that is being developed has to do this. Another thing that I also see happening in the X-ray spectroscopy community is there is this Athena type file format, which maybe you used. So another approach to do this is to go yourself to go to the process of taking your data and put it in something that is, let's say, more widely used than an HDF5 file format that ESRF uses. And then to have the analysis library be able to treat this more, let's say, general format. Maybe it's not going to be a standard for everyone, but at least it's used by the community. That's another way to approach the issue. Yeah, but we can, of course, that's something that can be done, can be solved. Okay, so I think my outline is out of the window. So, like, in terms of timing, so I just want to present to you what are the type of experiments you can analyze using this library. Of course, as I said previously, it's not only X-ray absorption that is measured at ESRF, you can also measure X-ray emission. And this is again on chromium 203. And presented here is the X-ray emission lines. You have the K-alpha, K-beta, and the K-beta valence score. These come from, again, this figure is taken from the same paper as before, which mostly deals with 3D transition metals, with K-edge spectroscopy. And you have, for example, excitation of the 1s electron here that is ejected from, so it's excited to the continuum. And then you have relaxation of different electrons from a 2p. In this case, you get K-alpha. From the 3p, you get K-beta, or from a hybridized 3D and 2p orbital, and you get this valence to core. So this gets you the different lines. And in terms of intensity, the K-beta is 10 times less intense, and the valence to core is 1,000 times less intense than the K-alpha. You see, as before, you need to import certain Python packages, and this is the syntax for that. You have NumPy, and you have now X-ray emission experiment. So you import these as we did before with X-ray absorption, and the idea is, as before, you specify file name and a scan ID. In this case, in this specific case, you have a single scan, which is the emission scan for this. It's stored in this file. The counters, because it's an X-ray emission experiment, you have the excess energy. The signal is the same as the APD, and the monitor is again I02. And now I'm defining a measurement. I specify the source, and I specify the counters. As before, I mean, in this case, is not much is happening. Here, it just reads the data from this one single scan, and it plots the X and the Y values. So you get one, you get the emission line here. However, a particularity in this experiment is that you can have different regions of the X-ray emission, which is measured in different scans. So this is something that I try to present in X-ray absorption with these for loops. You can specify a number of scan IDs, and then for each of the scan ID, you create a measurement. So the source changes, the file name stays the same, but the scan IDs changes every time I go through this. So it's going to be 4, 5, and 6. And for each of these, I create a new measurement, and then I append this measurement. So I add them in a list of measurements. So, and here is when I type measurements, I'm just going to have a list of 3 measurements. So you have 1, 2, 3. And these are measurements which each individually use the same file as source, but they use a different scan IDs. And if you plot them, so if you plot them, you have the 3 regions. So the like the blue is from scan number 5. You have this orange, which is from scan number 4, 5, and 6. And this is a way to measure X-ray emission spectra on, again, on ID26, because some of the regions require to be measured with more, like have the step size smaller or larger, depending on the region. So you spend, for example, a lot of scan points here in the valence to core region. Now to merge the measurements, you can use the merge measurements function, and then you provide the list of measurements that was created above. And in this case, it merges the measurements. It creates the X and Y, okay, X and signal, and then you have the black line, which is overlapping the initial scans, right? So now you have the black line, which is a merge measurement. To overcome this variation in intensity between the different regions, you can plot this data using log scaling on the y-axis. And now you have a log scaling, which is exactly the same scan as it's here, but now the valence to core region is more visible. And if you compare it with data, published data in this paper, where they also describe here how it's possible to do a background subtraction on the valence to core region in order to correct. So basically, we subtract the background in this case, and how you can fit to these points a background, and how this can be subtracted in order to get like the proper valence to core X-ray emission spectrum. Okay, so the particularity of this X-ray emission analysis is that you can use data from scans that do not overlap, and then you can merge them together to give you a final scan that you can also use afterwards to do some background subtraction, for example. Okay, so terminal is here. ID26 has, for a year and a half now, a new spectrometer, which can measure, which is for the tender X-ray regime. So it's appropriate to measure compounds containing sulfur, for example, or 4D transition metals. One particularity of this instrument is that it's all enclosed in a vacuum chamber. You have here the incoming beam, and then which is then analyzed by this by the spectrometer here, which has 11 crystals, and you have the analyzer, which is represented, which is here. So here we have a photo of the spectrometer. Maybe it's not that visible via Zoom, but you should be able to see it clearly when you're going to be able to download the notebooks. Again, the analysis of the data from this type of experiments has some particularities. In that, as I said here, for each scan, you need to build the signal for each scan for the individual data from each wire. So what I mean by that, let me just open the file so you're going to see more clearly what exactly. This one is it's in transition metal compound. So let's do a PyNCA. Okay, so PyNCA. So it takes some time to open. So the data itself is in scan number 2. So scan number 2, you go and then you have the Z energy text, that's the x-axis. And then you have these wires. So from each crystal analyzer, you get a signal. So this is one signal, and then so that's one thing. And the second thing is that you can have, due to cosmic rays, you can have spikes in the spectrum. And what you would want to do is to average the data from each of these wires, and then to also at the same time remove these spikes which are we don't want in the final data, in the aggregated data. So as before, file name, scan ID, and then you define the counters that you want to use. The signal now, as it is represented here, comes from a number of files, so from a number of channels. And the monitor also changed something that is called now I0T. As we did with PyMCA, it's possible to plot the data in each scan and for each wire individually. Now you have a single scan, but you could also imagine that you have multiple scans in the data. And this is what you're seeing here, is the data the same way you saw in, let me just make this a little bit wider. This is in PyMCA, and then, okay. So most of the scans don't have any issues, but you have this scan coming from seventh crystal analyzer that gives a spike here. So you want the procedure to remove these outliers automatically. The library provides a way for a measurement to find if there are outliers in the data. And you provide a threshold. This threshold is the amount of standard deviation that a point has to have from a median, and this median is calculated using a sliding window. So it takes the whole signal from a wire and it slides a window across it, and for that window it calculates the median. And for each point, it compares the value of that point with the value of the median, and if it's outside of this 3.5 sigma deviations, then it's is going to flag that thing as an outlier. Now, something that the library, because it's let's say relatively new, also because ID26 is not measuring, is not using HDF5 for a very long time. There isn't a lot of documentation. Of course, this is going to change, but the library itself is quite well documented internally. So if you do something like measurement, find outliers, and you put a question mark, and then you execute the cell, it's possible to get documentations about it. Maybe this was not the best place, but there is also online documentation. So let me see if I can quickly find the website. Excuse me. So this I need to type the ESRF. Okay. Okay, and then settings. Okay, I can put the link in the chat. So it's also some of the few things that you'll also be able to do. So it has some documentation here online, so you can do on measurements. It tells you, for example, what each of these classes does, and it says, for example, for a source you have provided a file name, or a identify the inclusion and exclusion. Inclusions is the scan IDs you want to include, and you can also, for example, include all the scans in a file that have, there are F scans, but you also want to exclude maybe number 25 or 35. So it's possible to do that. Then it provides measurements for X-ray absorption and X-ray emission, so XAS. So if I go specifically to X-ray emission, the one that I'm using here, and then I go to the, find outliers. Here I can click find outliers, and it tells you that it's using the Hempel filter, and each of the parameters of these functions is outlined. So the size of the sliding window and what the threshold for sorry, last. Okay, so this one. Okay, so I'm going to go back to the notebook. Close this. Okay, so I'm executing now find outliers, and then I go to the whole process of plotting the individual wires again. Now this one has selected a value of the threshold of 3.5 sigma and a window size of 25 points. But I just want to show you what happens if I change some of these parameters. So the idea here is to find the parameters that eliminate the outliers that you want. Maybe also in the future to have a more robust outlier detection, because for a human eye, is very clear which one is the outlier, but like for an algorithm to extract an outlier is not always that obvious. Okay, so when I was preparing these notebooks, I select the window size of 25, and then you have the outliers, which is identified. And then you can do remove outliers. So once you have the optimal parameters, you can call the method remove outliers. And once the outliers are removed, you can plot, as you did before, the measurement and the signal. And this is the final result, where it averages all the spectra that are here to give you the final X-ray emission spectra for this company. So again, the particularity of this example was that you had this the detector, which sometimes can be affected by cosmic rays, and you can have spikes appearing in the scans data. Okay, so the last example for this first part is to go to RIXS. To analysis of a RIXS experiment. Some of you have done RIXS measurements, or it's something very unusual?
Some have done, but I don't know if all.
Okay.
Yeah. You've also done some.
So not really. I mean, you don't usually do RIXS. I mean, they are still quite specialized type of experiments, so it's not all the time that are done. Most of the time is X-ray absorption. So in X-ray, when you do a RIXS experiment, you excite this time don't excite into the continuum like you do in X-ray emission. You excite into unoccupied orbitals, which are still relatively close to the Fermi energy. And then you measure the X-ray emission spectra. This is because of the similarity that exists between RIXS and X-ray emission. Sometimes RIXS is also called resonant X-ray emission spectroscopy. More specifically, what you do is that you position the incident energy at a certain value, and then you measure the X-ray emissions spectrum. So you excite with a very specific energy, and then with your spectrometer, you're going to measure an emission spectrum. And you do this for a number of incident energies, and what you end up, when you put all the data together, you get a 2D plot, or like a 2D image. Most of the time, you will see this in publications displaying as a plot of the incident energy and the energy transfer. The energy transfer is the difference between the incident energy and the emission energy. So it is represented here. So the energy transfer is this energy difference here. And maybe this is a little bit difficult to grasp, and I'm going to show you later the two ways to plot the planes. So maybe it's going to be more easy to understand. Like, you can have incident energy transfer. You can have also incident energy and and emission energy. So directly this omega here. Also, one thing that you will see in the publication is that the RIXS plane is going to be cut by different ways. You either do a diagonal cut in this type of plane where you have energy transfer. A diagonal cut in this energy transfer is going to give you this high resolution detected high resolution fluorescent detected spectrum, which is this absorption spectrum where you see this a reduction of the line broadening compared to transmission experiments. Another way to think of this type of experiment is that you are measuring the X-ray absorption spectra with your spectrometer fixed at a certain emission energy. So you fix yourself on, let's say, on the maximum of the K alpha emission line, and then just measure the absorption spectrum. So you just scan over the incident energies. Okay. The process of analyzing RIXS data is a little bit different, but in itself, but starts the same. You have to import all these libraries that you need for data analysis. And in this case, we have RIXS, which is the name of the class to deal with this type of experiments. The experiment itself is on a nickel metal organic framework, and in this case, the scan IDs, which are here from 3 to 83, what they actually give you are these horizontal cuts into the RIXS plane. So scan number 3 has a very specific incident energy, scan number 4 has the next incident energy, and so on and so forth. So each scan provides you an emission spectrum at that incident energy. You still have to specify the counters. You have the X with the HDH energy, the signal, and the monitor, which is very similar to an X-ray absorption experiment. Now, seeing that most of you are not very familiar with Python and notebooks in general, maybe this part is going to be even more confusing because I put a note on plotting 2D data. So there are like two ways to plot 2D data. And what you have to know is that depending on the option, so even if you don't do any experiment, so this is not necessarily, this is data that is measured, but even if you just plot a simple image, there are a lot of options into these plotting libraries that can change the way the data looks on the screen. So here I'm using these two ways of plotting the data, but I'm going to change a little bit the way some of these the parameters of this. So first I'm going to change the number of levels. So here I changed the number of levels of the plot on the left-hand side. You already see that this looks different from what I had initially and looks different from what I had on the right-hand side, which at the beginning were very similar. I hope to see this via Zoom, but it's a bit, because it has compression algorithm and so on. So this is similar to what you would find in maps where you have this contour plots that you usually represent altitude. So each of these contour plots has a various energy for it. So it has a different energy for it. So as you change these, is going to change the number of contour plots that they are plotted. So if I put a very large number of contour plots, you're not going to see the individual plots themselves anymore. So okay. The next thing is that they also have, of course, this is not a continuum of points, and plotting functions like emshow can have different ways, different algorithms to do the interpolation between the points. So you have, let's say, a number of, let's say, 1,000 points between them, but to show this image on screen, you need to interpolate the data between them. So if I do, for example, if I interpolate it by linear, you get this type of plot. But if I do nearest, you'd see that now the image here becomes more pixelated. So this is actually closer to the real data, and what the plotting library does, it changes the way the data appears just by simply changing the interpolation. So here I hope you saw this the effect here on the right-hand side. Okay, so this is something to keep in mind in general when you're plotting data, and the fact that you are seeing all these options. I know it can be intimidating because we go back to the discussion that there are a lot of options and a lot of things that you need to take into account. But if someone else is doing this in a graphical user interface, is actually more you don't know what's happening. So at least the advantage here is that you see, and if you read a little bit of the documentation, you can understand what's happening behind the scenes. Okay, so now I'm going to go back to this emission energy versus energy transfer plots. So here is the signal that the RIXS plane for this nickel MOF, and I'm plotting the two planes here. Sorry, I'm just going to, okay, maybe I'm going to leave it like this, doesn't matter if the levels are not that, because now it's a little bit even more visible. So the incident energy, the axis doesn't change. What changes is that now I'm plotting the emission energy here and the energy transfer here. The energy transfer is just, as I said, as it's said here, is the incident energy minus the emission energy. So if I take, for example, if I imagine that here I have the cuts, the vertical cuts here, I have an incident energy. And if from this incident energy, I subtract all the value of those points, you would end up with something like this, okay? So this is the different ways to plot the plane. You are going to see both of them in publications. Also, if you measure samples that are very sensitive, you sometimes do each of these vertical scans in the RIXS plane. You do them on a different point on the sample. You can also apply, using the library, you can apply a concentration correction. So here we plot first the uncorrected plane, and then we do a concentration correction on the plane, and where you provide here the index of the scan, where you do where you have the counts for each of the points that you measure in the plane. So these counts are going to be used to divide the intensity of each of the emission scans by it, and this is going to give you something that it's constant, is correct for the heterogeneity of the sample. Because when you do a pellet, you don't always make it. It's not always, doesn't have locally the same concentration. So then you scan a different point on the sample. So you see, actually, it's, with this type of lower number of levels is maybe more obvious. You see that applying a concentration correction, the scan on the left is not concentration corrected. The scan of the right is concentration corrected. You can also see it changes the way the RIXS plane look. Okay, everything is relative. In some cases, if the pellet was very homogeneous, like maybe it was in this case, you are not going to see a lot of change between the two spectra. But in case you have a heterogeneous sample or a heterogeneous palette and measure at different points of the sample, then you're going to see a much larger difference between these two. So now that you did the concentration correction on the sample, you can do these cuts, which are that I showed initially. I'm just going to go back quickly to show you it again. So you have a diagonal cut, which is represented here, which is this HERF spectrum. You can do a vertical cut and a horizontal cut. Sorry, an horizontal cut. So when you do a vertical cut like this, you get the energy transfer spectrum, which sometimes is similar to a emission energy. Sorry, to an emission spectrum. And you can do also a horizontal cut, which it just gives you this constant final state energy. This is not that used that much. Most of the time you will use either the diagonal cut, which gives the HERF, or the vertical cut, which gives you this sort of emission spectrum. So it's possible to do the cuts quite easily. You just specify what type of cut you want to do and at what energy. So I'm doing constant emission energy, constant incident energy, and constant energy transfer. And then when you do the cuts, you can plot them. Now I specifically plot here only the constant emission energy and the energy transfer. One thing that actually is very important when you measure this HERF data, X-ray absorption data, because it's a diagonal cut in the plane, the way this HERF spectrum is going to look depends a lot on where you do the cut. So you have here this blue, orange, and green cuts, which are represented on the right-hand side. And you see that the way, for example, the blue spectrum looks significantly different than, for example, the green and the orange. Even the green and the orange, which are relatively close to each other, they look quite different between them. But more striking is the difference between the blue and the orange and the green. So this highlights that sometimes when the HERF data is measured, it's very important to position at the proper, let's say, at the intensity of the emission line to actually get a proper diagonal cut in the plane at in the maximum of the emission line. And this is also why if you're ever going to measure RIXS, if you're doing RIXS measurements, is always going to be important that you measure, is going to be suggested that you measure the full RIXS plane, because the analysis is going to be different. I mean, it's going to, if you measure a simple cut, you don't have the full picture, basically. This is what I'm trying to say. If you measure a simple cut and you say you see a spectrum like the blue one, you can get to some conclusion that this corresponds to a change, whatever, change in oxidation state or an oxidation state that you are not, that is different from the actual sample. So, and because most of the time you don't measure in transmission at ID26, for example, this is something to keep in mind. Okay, so I went a little bit quickly on these notebooks. There aren't that many questions. So if you have any questions before we take a short break, and I can show you quickly afterwards how you can do simulation for some of these spectroscopies. So if you have any questions, no, okay. So if it's fine with you, we can take a break now, and we can meet in, let's say, 11 o'clock, if it's okay.
Okay.
Okay. So see you in a bit.
Marius, maybe a question,
Please.
general one. So your code was specifically developed for ID26, or it's big? Yeah, because like ID26, ID20, they have different ways how they acquire the data, different detectors.
Okay, so the code is developed based on data from ID26 because the idea was to have some data analysis tool for the new way to acquire the data using HDFI file format and so on and so forth. In principle, there is nothing particular to doing this type of XAFS data reduction to ID26. So I think a user that goes to another beamline, like FAME or something else, they will do exactly the same type of things. Maybe what will change are the counters which define the X signal and monitor data. ID20 and in the same category is also ID32. They are very particular beamlines because they stand out from all the, like most of the spectroscopy beamlines with ESRF, because they do experiments which are like the way data needs to be processed is very different from most of the other beamlines. For example, ID20 and also ID32, they measure, they have a detector, they have images from each of the detectors, and they do a reduction, data reduction of the images to get the spectrum. So the analysis for these beamlines is different, and both of them have developed their own software to do the data reduction. The goal with this library is to have something that is, let's say, applies to the other 90% of the beamlines at ESRF. And just yeah, maybe to go one step further, as I said in the beginning of in the presentation, there are quite a few tools that do also user interfaces that do data reduction for absorption and XAFS, but not that many that do for X-ray emission in RIXS. These are not very complicated things to do, but if everybody would have to repeat the same steps of coding, read the scans, normalize the data, do the averaging in a certain way, this can lead to errors, and also it's not very productive. So it's better to have this type of notebooks which contain how to do a data analysis on an X-ray absorption experiment, and then change that.
Thank you.
Okay, so I'm a little bit behind schedule, so in the next part I'm just going to go maybe quicker. It's also the part that actually is more complex than the previous one, so it might even be. Hopefully, I'm still going to be able to share some information that is going to be useful to you. So when you finish your experiment, you did the data reduction. You get your final spectra of the samples, and most of the time, to understand something about your sample, you would compare it with measured references. So to give a concrete example, if you measure an iron compound and in the same experiment, X-ray absorption of an iron compound, in the same experiment, you would measure these oxides. And for each of these oxides, you know the local coordination of the iron, you know the oxidation state of the iron. So there's quite some information that you know about these oxides. And now you know how the spectrum looks. And by comparison of your, let's say, unknown species sample with this spectra, you can say, this looks more like an iron 2 or some iron 3, or this looks more like a tetrahedrally coordinated iron. This is what it is usually referred to the fingerprint approach. Now, the other way to go to about this problem is to use theoretical calculations do this type of analysis, like to understand something about your sample. Now, there's quite a few codes that you can use to do this theoretical calculation. You have specialized ab initio codes, like one maybe that you know is the FDMNS, which is developed by Yves Joly here in Grenoble. You have some generic ab initio codes which were repurposed to do spectroscopy calculation. I say repurposed because they were initially developed to do UVV spectroscopy, but the only thing that changes when you're trying to do X-ray absorption spectroscopy is that the excitation energy is different. But other than that, there's not that big of a difference compared to UVV spectroscopy. And then you have what are called semi-empirical multiplet codes. Now, the particularity of these codes, that also, again, some of you might know, for example, CTM for XAS. I mean, it's a small audience, so maybe it doesn't speak to everybody. But these are software. These are programs that are developed to be relatively fast compared to the previous two, with the caveat that you have to input some parameters. Another difference is that compared to the previous two, where you just give a three-dimensional model of your system, you give it to the program, and the program calculates the spectrum, to put it simply. In this last class of software, you do not put the 3D position of the atoms. You just describe the strength of the interaction that you have in your system. So you can say, you know that you have an octahedral coordinated iron, for example, and then in that case, you give to the program the 10dq value. So the value, the splitting of the d orbitals in your compound. Now, one program that is now used more and more to do this type of calculation, and this is the type of calculation that I'm going to talk to you briefly about, is a program developed by Maurits Haverkort, which is called Quanti, and he's at Heidelberg University. Now, Quanti is very powerful and a versatile library. So it's if you want to have a comparison, it's similar as an idea as what you've seen for this data analysis with DAX. So you have a library, you build your calculation program, and then you run this becomes something that you run, and you get the output. So it's not the user interface. It's not, you have to write code, so it can be intimidating, and this is already something that it appeared also in the discussion today, that writing code is not always the easiest thing to do. And it's also the type of thing that can lead to a lot of errors, because you can make small errors in the way you write the code, and you not know why you do not get the spectrum. So due to this limitation, I wrote a user interface around Quanti, which can be used to perform semi-empirical calculation for different types of spectroscopies, like X-ray absorption, XPS, and RIXS. And you can have elements in different coordination, octahedral, D4H, and so on, like tetrahedral symmetries. So what you can do with this, you can do all these type of calculations. You have some output of how the calculation is going. And in the latest version, I also added the possibility to actually run this type of calculations from the notebook. You can find the code here. This is the original code, where you can also download binaries for different operating systems, for Mac OS and Windows in particular. So I'm just going to show you quickly how the interface looks, and then you usually don't start it like this yourself when you install it, but this is how I started, because I'm working in a development environment. So when you start it on your local computer, after you install it, you see something. You would see an icon. You double click on it, and this is what you would show. It will show to you. So very briefly, you can select the absorbing element, the type of experiment you want to perform, and the different parameters about the energy range that you want to, in what energy range you want to calculate the spectrum, broadenings, Lorentzian and Gaussian. And when you click run, it gives you, this is an L23 absorption spectra of nickel 2+. Okay, and it gives you this. So you have a different ways to interact with the spectra. Let me just show you, for example, an iron, maybe because a K-edge spectra. So you can select iron 2+. Let's put iron 3+ because it's easier. Then you click run, and I'm going to unselect the first. So this is the type of K-edge spectrum that you can get for an iron 3+ in octahedral environment. And now I'm going to go back to this idea of you do not give 3D coordinates of the atoms, but you just specify parameters of what is used in the calculation. And in this calculation, the crystal field splitting between the two sets of d orbitals in octahedral symmetry is set to 1 eV. So if I put 2 EVs, which is going a little bit far, if I click run, you see that the initially coalesced peaks, they will split, and you get an indication that the octahedral splitting influences the way the spectrum looks. And by doing this, for example, you can do a simulation with different values of 10 dq, and that's going to give you, and then compare with what you're obtaining in experiment. And based on this comparison, you will be able to say something about the octahedral splitting in your sample, for example, if you know that you have an iron 3 in an octahedral environment. So this is the type of process that happens when you do this type of calculations. You start with an hypothesis about what is your absorbing element, which in principle you should know, something about what is the oxidation state. And then this also can be something that you vary in the calculation. For example, if I were to do iron 2+, the same idea, and then, for example, I select again a 2 EVs, and then I click run, and I'm just going to plot only the iron 2 and iron 3 spectra. You see that the two have quite different absorption spectrum pre-edge region in the K-edge. So you go in this process, you change oxidation state, you change some parameters in the calculation to give you something that resembles as close as possible to your experiment. And based on this, you can draw some conclusion of what the oxidation state of your sample might be, what is the crystal field splitting, and other parameters which you might be interested in when you're doing this type of experiment. So this is not, so schematically what happens in one of these type of calculations, if you're, for example, if you're interested in L2-3 edges of transition metal ions, you get an excitation from the core hole 2p to a 3D orbital, to a 3D vacant orbital. And then this leaves you with 2p5, so with the core hole on 2p. So what happens in the calculation is that for this electronic configuration, it calculates the energy of all the possible ways to combine the electrons into these states. And then it does the same for the electronic configuration where it has a core hole. And then it says, because it's an L2-3 spectroscopy, it does all the electronic dipole transition. And all of these electronically allowed dipole transition will have a certain intensity, and this will give you an L2-3 edge absorption spectrum. In this case, I think it's an iron. So it's a rotated. Of course, with other type of spectroscopy, like the cages, the excitations happens from a 1s core orbital, but in the calculation itself, the same thing happens internally. Now, this is a bit mathematical, but it's just to tell you something about how internally what you have is, in principle, the Hamiltonian is what describes your system as a number of terms which correspond to something that as you would have the isolated ion in vacuum. And then on top of this, if you add a crystal field, then you have something that is closer to reality. So when you add a crystal field, you just put around your atom something like electric charges, and this will influence the orbitals of your absorbing atom. They will be split, for example, in the case of a 3D atom. I mean, will split in two sets in the case of OH symmetry. Then you can allow hybridization. Hybridization simply means that you, in addition to having some electric charges, the orbitals of the ligands will be able to interact with your metal, for example. And by hybridizing, they were going to influence they were going to influence how the spectrum is going to look, the absorption spectrum is going to look. You can have a magnetic field, or you can have an exchange field between the different centers. Now, you do not put a three-dimensional structure, and this leads to a set of parameters. Because of this, you have a set of parameters to describe your system, and these are these electronic repulsions between electrons. You can have spin-orbit coupling between the spin-orbit coupling constant, crystal field parameters, and where you can take all of these initial values, for example, from other type of experiments, EPR, optical absorption, or even ab initio calculation, and these hybridization parameters. So while these calculations are fast, relatively fast compared to, for example, a DFT calculation, you have to keep in mind they are parameterized type calculations, and in order to, what you have to do is to change these parameters in order you need to vary this parameter in order to get a better agreement with the experiment. And following this improved agreement, you can say something again. You can say something about your sample. Do you have any questions right now? No. So if there are no questions, I just want to go through to show you how you can perform this calculation in a Jupyter notebook. So as I said, there is also a user interface in case you want to try running this calculation in a user interface. As I try to highlight in the case of data analysis using the Jupyter notebooks, while I know it's more complex to do this in a notebook than in a user interface, there is great power in doing this in a notebook, because it's possible to do the analysis, for example, quicker for a larger number of samples. In the case of calculation, you can vary parameters more easily in order to find the best agreement with an experiment. So that being said, let me just open the notebook that I prepared. So this is a first multiplet calculation using Jupyter notebook. We don't need as much in terms of scientific libraries other than to import from Crispy, which is the name of this user interface to do this semi-empirical calculation, to import the calculation and the config. The config we need to just set some like not to shift the spectra and not to remove the files after the calculation. It's not really, this is actually not really mandatory. So Here you create, as you did in the case of the measurement with the DAX, you create a calculation. You specify what absorber you have, the type of symmetry, and the type of experiment that you want to do. So by default, all calculations are done at a temperature of 10 degrees and without any magnetic field. So it doesn't do, they don't, which is something that most of the, if you're not doing ECFCD, you don't need
10
this.
degrees in Celsius or Kelvin?
Always in Kelvin.
Okay.
Sorry. Yes. Where this temperature is important is that is when depending on the temperature, those states that I show you of the electronic configuration, they are going to be populated differently. So the final spectrum is going to might look different if you do it, which is also what you have in experiment. It might look different if you do it at 2K or if you do it at room temperature, because the states will have a different population, so the spectrum will change.
Can you also go to higher temperatures?
Yes, there is no limitation, so you can go to whatever temperature you want. It's just application of Boltzmann statistics. You calculate some factor that is used when the final spectrum is built, let's say. So it's absolutely.
When you call your calculation nickel 2+, this means that this is a nickel 2+. So you would have a nickel, I don't know, 1+, 3+. Or...
Yes. So
which elements are in?
In terms of oxidation, excuse me, sorry. Sorry.
Which elements are in? Only 3D or? Now, can we use platinum? I guess not.
Yes.
Here we have a long list.
There is platinum. So a bit of a disadvantage of using this in the notebook, you do not know everything that is available, but in the interface, you can use platinum. You can have the different oxidation states that are there. I think it should cover most of them. And actually for platinum, I don't know which one is the most common. Then you can do XAS, and then you have different edges. So
okay.
And okay, if there is something that you don't find, again, I would be very happy to add it. So you define here the element. Then you do calc.spectra, and actually just let me do this before, because when doing this in the notebook, as I said, there is a learning curve, but there are a few commands that can help. For example, if I do a dir calc, I get all the things that I can use from this calculation. So if I do, for example, calc, and then I say, give me the Hamiltonian, the spectra. So by default, it calculates the absorption, but it does isotropic absorption. There is also absorption along a given incident vector. I'm not going to, because it becomes more, because you have a difference between if you do the calculation for powders or if you do for a single crystal or a thin film. So it's a little bit of, but most of the time a lot of people are interested in isotropic samples, so powders, for example. Then let's say you want to also enable the calculation of XMCD spectra. Then you say calc spectra and enable, and then you see that now you have true and true for this. Because I want to do also circular dichroic, I need to set to the calculation a magnetic field. So I set calculation set parameters and magnetic field. And now the magnetic field is changed to 6.5, which is 6.5 Tesla. I should have mentioned that. Something that changes the way a spectrum looks is the Lorentzian and the Gaussian broadening. Now, the Gaussian broadening has to do with the experimental resolution that you have. So this depends on the experiment. The Lorentzian broadening is related to the core hole lifetime. So if you do something that has a short lifetime, then the like 1s core hole that is going to have many, let's say, probability to be filled. This can be quite a wide full width half maximum. So we change this to some values which are like the Gaussian you probably get when you're doing the experiment, the Gaussian broadening. The Lorentzian broadening is usually set for you by the interface to some default values. You change this in order to increase the agreement with your experiment. So here I'm changing the Gaussian broadening, the Lorentzian broadening with the values here. The spectrum is going to have 2000 points. This is just for information, like the same type of information you find here, basically. So I'm working on this x-axis. And then here I go through some of these parameters that define the Hamiltonian. These are the Slater integrals and the 10dq value and the number of states that I want to calculate. Now, if I would do I want to quickly show you this in the interface, right? So let me go back because I really think that while I agree that it's difficult. So this would be the default state of the interface. Now, okay, so first thing I want to do, so is Nike 2 plus okay. First thing I want to do is to enable circular dichroid. Okay, this is not very complicated. I just click here. Then I have to go to change the magnetic field. I put 6.5. Then I will have to go to change the broadness, 0.24. And then I'll change also the Gaussian broadening. So the Lorentzi's is 1. And the Gaussian broadening is 0.24. Okay, so this is not very complicated, but then I want to change some of the parameters in the Hamiltonian. So I say FK, GK, and 10dq. Okay, so I have the scale factors that I said, so 0.7. So what you will notice, I pointed at the screen. So what you notice is that these scale factors will change. So 0.7. 0.7. This changes the interactions in your system. And then I have to say 10dq is 2.8. So I go to the crystal field and I say 10dq is 2.8. And the number of states is 3. So I don't want to calculate auto. I just want to put the number of states to 3. Okay. So this is what I had to do in order to set all the parameters in the interface. Alternatively, I could just do it like this and just execute this cell once, and all the parameters are changed for me automatically. Now, what's nice is that once you can do this for a very, very large number of parameters, and you can do parameter scans like I'm going to show you in the next notebook, which makes all this scanning of the parameter space much more convenient with the notebook interface. Now that you set all the parameters, you can look at the input file. So if this is a quanti input file, and it's a quite long input file. So this is for you to. I'm just printing this here to see there are quite some technicalities involved in doing this calculation if you were to do it yourself using the quanti, which is. So it's a quite complicated info file. Even though it's commented, it's not that easy to, let's say, to do. So once I'm happy with the parameters that I set up, I can do calc run. Okay, I'm just going to take this. The calculation is normally pretty fast, and then I insert cell below, and then I print the output. And this is like it tells you the splitting in EVs, this 2.8 value that we set between the EGs and T2Gs, some information about the expectation values of some of the SZ, LZ, and some of these operators that you might be interested if you do, for example, XMCD measurements. And finally, when I'm satisfied with all, I can just plot the spectra. And you have all the spectra that have been calculated. There is isotropic absorption in blue. You have the right and left circularly polarized experiments. And then the difference, the two, is going to give you the XMCD signal. And you can always go back change the parameters, rerun the calculation, and see how that affects the result of the final spectrum, how it will affect the final spectrum. So it's exactly about this, how easy it is to vary these parameters that I want to discuss next, because these are parameterized calculations. As I said, you have to change them in order to get a better agreement with the experiment. So we import some of the required libraries. They're very similar to the ones you had before, but now you have this calculation. Before you had this DAX measurement and so on and so forth. I want to show you here a calculation of an iron 3+ ion in octahedral symmetry. So I do the calculation. So and with the next cell, I'm going over a series of 10 DQ values. So this is the value that, as I said, gives you the splitting between the T2Gs and EG orbitals. And I'm going to scan this value. I'm going to take 4 values between 0 EVs, that means that they are not split, to 3.6 EVs, that means quite significant crystal field splitting. And I'm going to run the calculation for each of these values, and I'm going to plot the spectrum. So here I'm setting the 10 DQ value to whatever this function gives me. And let me just quickly show you what this function gives. So I'm just going to insert a cell below, and this is a NumPy function and linspace. So this gives me the following value. I could have, so it's giving 0, 1.2, 2.4, and 3.6. I could have easily taken these values and instead of these, put here like this. Okay, so I'm taking 10 DQs. Sorry, I'm taking 10 DQs of 0, 1.2, and 2.4, 3.6. I'm running the calculation. I extract from the spectra that are calculated, because as you've seen previously, there are can be quite a few that are calculated. I extract the isotropic absorption spectrum. I say that X is equal to X in this data, and then I plot. Okay. And then I also, finally, I also take the X and the signal of this calculation, and I save it in a results list. Yeah. Okay, so let me run the calculation. The calculations are going to be quite quick. So for all of those values, those 4 values, I calculated run 4 calculations. So sorry, 1 calculation for all of these values. So you have calculation 1, 2, 3, 4, and the plot shows you how a 10 DQ value changes the shape of the absorption spectrum from iron 3+. And just let me, because I think it's a very interesting thing about to understand something here. You start from a 0 EV spectrum, which you have a single peak. Then, as you increase the 10 DQ, you get the 2 peaks, which are which correspond to this transition to T2G and the EG orbitals, which are 3 and 2. As you increase the 10 DQ, these peaks will be split further. So and this gives you an idea that the splitting of these peaks is actually related to the 10 DQ value. So it is related to the crystal field splitting. And what happens in the last spectrum, red, which is totally different from the previous 2, for example, from the green and the orange one, is that while initially your system was a high spin iron 3+, when I increased the 10 DQ quite significantly, the iron goes in it's still an iron 3+. It still has 5 d electrons, but it has shift to a low spin electron configuration. And the spectrum here in red is the one that is commonly seen for low spin iron compounds. So Of course, I could have done all of this in the interface, but it would have required a little bit more effort. And the advantage of doing this in a notebook is that it's very reproducible. And if I, for example, if I want to investigate, let's say I want to investigate where, at what 10dq you have this spin transition. And for this reason, I put something like, okay, maybe 8 values. So I'm going to, by a simple click, by simple change, I'm now scanning 8 values in this interval, and not very easy to see, but it's somewhere between 3.09 EVs and 3.6 EVs that you get the spin transition. So the iron iron 3 plus would go from a high spin to a low spin return configuration. With an interface, if you don't have some capability of scanning these parameters in the interface, which for the moment does not exist because it's significantly more difficult to program, it's more difficult to do this type of manipulations, so this type of experiments. And these are needed when you do semi-empirical multiplets because you want to vary parameters, you want to know what values give you a better agreement with the experiment. Something that I did not touch upon this yet, until now, even in the previous part and in the second part, is like, how do you get data out of all of these calculation and data reduction? You have functions. For DAX, you also have something that just measurement saves spectrum and is going to save the spectrum to a file, the reduced one. In this case, you have NumPy functions that save arrays to text files. So for example, here I save the results of all these calculations. I save them in a file which is called results.dat. And when I do an ls, I just see this file here. And let me just go quickly to see if I can open. So now you see that the file has appeared. In principle, should be able. You don't see it because it's wrapping the lines. So for each of these calculations, you have an X and Y repeating. So now you have 16 columns, and that's why they are being wrapped. But I made, so X signal, it's a header, it's signal, and for 10dq value of 0, X and signal for 10dq value of so on and so forth. And then, of course, you can recover this data and plot it with something else if needed for a publication. If there aren't any questions, okay, it should have been 5 here, not 6. There aren't any questions. I would like to just show you an example from a publication where they use this type of calculations to understand something about the crystal field and covalence effects in uraniums. When it's possible to do this high energy resolution fluorescent detection, X-ray spectroscopy, you get an increased this sharpening effect, which compared to a classical X-ray absorption spectrum transmission, for example, or in total fluorescence, you have features which are more easy to distinguish. Like you can say something about like maybe the nature of the crystal field splitting in some of these compounds. In this publication, they measure the X-ray absorption spectrum, this HERF for a number of uranium compounds, and they used crystal field, they used semi-empirical multiple calculations to see how they can reproduce an experimental spectrum. What do they need to include in the model in order to reproduce the experimental spectrum? And I'm going to show you how you can do exactly the same calculations in the interface. But before that, I just want to point out the different approximations they use in the paper. So in red, you have the calculated spectrum, which is an N4H for uranium 5+. And the first calculation here on the bottom is the atomic calculation. This is a calculation when the uranium 5+ is considered to be in vacuum. this is a very simple model because it excludes all the coordination environment of uranium. And while for lanthanides, it's been quite accepted that the environment of the 4F orbitals is not important. It does not affect the spectroscopy that much. When you go to actinides and 5F elements, you see that something like the environment, the ligands around the atom can have a strong influence on how the spectrum looks. To take this into account, they added to the Hamiltonian of an isolated ion, they added the crystal field splitting. And with it, you see that between these two spectra, you have some differences. And in particular, now this shoulder of the main peak is better reproduced in the calculation compared to experiment, compared to the atomic calculation. Finally, they were even able to say something about what are called charge transfer effects, which are features that appear in this type of M45 spectra at higher energy. These are transitions not directly into the 4F orbitals, sorry, in the 5F orbitals, they are transitioned into hybridized orbitals between the 5F and the ligands. Okay, so these are the three spectra that have been calculated in the manuscript, in the paper, and we do the same thing. So you have a calculation of uranium 5+ and the type of edge they want to calculate. The Lorentzian broadening plays an important role here. Gaussian also. I define the start and the stop because by default I need to focus myself on the M4 edge, and by default the program is focused on M5. So it's not possible to put the two of them because they are quite separated. It's not possible to put two of them on the, let's say, on a 20 eV energy range, because these two are sometimes have tens of even hundreds of eV separations between them. So I just redefine what the start and the stop value of the x-axis are, and I set some parameters. Okay. I create an empty dictionary to hold the results, and then I calculate the atomic. I see by default the program, in addition to the atomic term, it also has a crystal field term. So my first calculation is to disable the crystal field. So I don't want any influence of the ligands. Then if I look again, I disable this term, and now I have false here compared to true here. And then I run the calculation. So again, the calculation is quite fast. I'm going to get the calculated data, and I'm going to save it for later. I'm just going to quickly scroll at the end, and I'm just going to plot the spectrum. Okay, so this is the atomic spectrum that is very similar. It should be identical to the one that they had in the calculations, which was here. The next step is to do the same calculation using the crystal field splitting. Now, when you do actinides or lanthanides chemistry or like spectroscopy measurement, and you go to the literature, you see that the crystal field splitting for this type of F elements is expressed in Y-borne parameters, which are B40 and B60. These parameters can be used to calculate the energy of the 5F orbitals when they are split in an octahedral crystal field. So the equations are here. And so these are the mathematical equations written with LaTeX. So this is, again, the nice addition of using this type of notebooks. And then you have the parameters that I took from the publication of B40 and B60, and then I do the calculation using the equations above. I do the calculation in the notebook, and then I can pass those values to the Hamiltonian. So I'm setting the parameters, and then at the same time I re-enable the crystal field because I want now calculations with the crystal field, so with the point charges around it. Again, the calculation is quite fast. I save, so I get from the calc spectra, I get the calculated data. That data, I can address different spectra, like the isotropic absorption and the X value, and I store it in an X in this X parameter. I do the same thing for the signal, and then I put the whole these two values, I put them in the results, and I label them as crystal field. Now I go back to I go down to the plotting, and now I have two calculations. I have the atomic and the crystal field in these results. So now when I execute the cell again, it's going to plot an overlay of the two. And next, similar to what they did in the paper, is to calculate the ligand field spectrum. Now, these notions of crystal field and ligand field is, you have to see them as two approximations to how the environment is treated. Crystal field is very rough, it's just point charges around an absorbing atom. Ligand field, you allow the ligands to interact, the orbital of the ligands to interact with the orbitals of the absorbing atom. Because you define such a complex interaction, you add such a complex interaction, there are quite a few parameters that need to be considered. All of the values that I present to you are from the publication. How did they arrive to these values? My assumption is that they took some initial guesses that they built either from looking at other publications or by simply just starting with something that it was reasonable. And then they varied these parameters to get better agreement with the experiment. The spectra of these uranium-5 compounds and uranium in general, I think the effect of a ligand field treatment is not that visible in the spectrum. So let me say what I mean. I think if you compare what they are called a charge transfer, which is equivalent to a ligand field calculation, and a crystal field calculation, aside from a very small ripples, like very small peaks here, there isn't much of a difference between this and this. And also in experiment, it's a very, very low intensity signal in this region. So what they are trying to reproduce is this region. They succeed to some extent, but I think in this particular case, it's not that clear cut. So it's not that obvious that you need such treatment of the system. If you go to, for example, 3D transition methods, or if you go to 4D transition methods, where the hybridization plays a much more important role in the whole description of the system, then you will see a very, very strong influence of this in the appearance of what are called charge transfer peaks. In addition to requiring more parameters, I mean, already you see that even only to add this ligand field interaction, you have to add quite a few values. You have to change quite a few values. The computational time changes, and I think I did a few tests. So compared to under a second computation time, this one, if I'm going to run it, is going to take 10 minutes. Only because I'm okay, 7 minutes. So this was only because I'm adding to my Hamiltonian, I'm adding a term which is quite difficult to calculate and which significantly adds to the computation time. So I'm going to leave this to run. When it's finished, I'm going to add it to this plot, and maybe we can better see the differences between the different type of ways to calculate the spectrum. I would suggest that in the meantime, if you have any questions, any type of questions, I would be very happy to answer them. Even if you have questions about calculating X-ray absorption with other types of code or about data processing in general, I would be happy to answer them. or maybe if you feel inclined, you can give me feedback. I know that I'm under the impression that maybe this tutorial was not precisely what you expected. So since it's the first time that I'm doing this tutorial in a Jupyter notebook, I usually do tutorials in a graphical user interface where people can focus on the let's say physics or like simulating the spectra and less on writing Python code. I would be very happy to hear feedback, of course.
Yeah. You see, the problem I see with this notebook is that, of course, you know all your commands, but if you don't are not familiar with all these Python packages, you don't know which commands are available. Which it's very nice to see you typing in things and changing things, but if you don't know about the commands available, let's say have a list of commands you can use, it's very difficult to use that for your own work. If you sit at the beamline, for sure, then you can always manipulate and analyze your data. That's fine. I think so for data analysis direct at the beamline, I see it quite useful because it reports essentially what you have done. So this is what I like. It writes like an internal notebook which you can take home then and can see finally what you have analyzed. But if you really would like to analyze data from other places compared to from other beamlines, from other trips, it will be very difficult to use this type of software because, let's say, the documentation is, at least what we have seen, is not really there.
Mm-hmm. I agree. So you the best, I think, from your perspective, the best thing to do is to have more extensive documentation.
For me, in the end, I'm a little bit old school. In the end, I will use one with a graphical user interface, I guess.
Graphical user interface. Okay.
Because this is when I use LARC, for instance, or the other, also the Athena. Now I was thinking to use more LARC because it seems to be more, let's say, a little bit quicker and more modern. Well, it's quite clear what you do. You get your data, you make a baseline subtraction, you make a Fourier transform, you do a FF calculation, you fit the thing, and then you get your data for, if you do a standard EXAFS, which follow the same procedure like an Athena. But in this kind of programs, I'm sure you can also do that, but it's a little bit, say, not user-friendly enough.
I see. But
what I really like, and I would like to make this point in the end, is what I really like is if you sit at a beamline and you document all you're doing. I think this is if you write like a journal what you have done when you do the experiment. So when you come in the beginning of your experiment and you open a Jupyter notebook and then you start loading your data while you're doing the experiment. So you don't write a written lab journal, but you do it in this way and you see always how it's documented. I think for this type it's useful. So
okay.
for less writing an online beamline, let's say an online lab journal, because we were usually writing our online lab journal into a Word file, because you need one lab journal which you can then take together with your data. And handwritten is one option, but because we have many different experimenters over the night, during the day, so we usually write a text file, usually in Word, where we say we measure at 10 o'clock in the night this sample, and then we change and we put in different gases, and we then do this, and then and at the moment we just say, well, then we measure file number 712. If you then have this Jupyter notebook and you say, well, we measured file number 712, and this is how it looks like, I think that's a nice feature. Mm-hmm. They can look through afterwards while you do the experiment, or for instance, we do the experiment and the night shift goes home, and the guys on the day, they don't know how the sample was looking in the night, and they can easily look at the sample and say, okay, now we have a problem, or it looks better or worse, or we have to change sample. So for documenting actually what you're doing while the experiment is running, seeing not only writing in what you have done, but also, well, I can put on my camera so you see me once. That you can
be better do it like this. Yes.
Yeah, it's more personal. I know that when you do your experiments, you follow exactly what you have done, and you say, okay, it's like, I think for an online journal at the experiment, it's a very useful thing, and it should be really implemented, because then you can see what happened. You can compare it's not only documentation what was done, but you can also see how the spectra look like and how it developed. And if something goes wrong, you see, okay, this spectra got wrong, we have to remeasure, or even you can see, does it look okay? And we decide that we remeasure the sample or not. So for this, I see it very useful. For analysis afterwards, I'm a little bit, I see it not so useful, but I know what Dimitri thinks.
Well, Andreas, I think it's inevitable. I'm also not an expert in Python, and it also gives me troubles, let's say. But if you are going and measure now a lot of spectra at once, like quick exhaust or energy dispersive, where you have thousands, I do not see any other way as to employ Python. But here maybe we have a good example with respect to graphical user interfaces, which is ProXAFS or Pro Quick Exhaust code by Adam Clark from PSI. The only problem is those codes are specialized, tailored to a specific beamline, basically. And it's here in a similar situation where, with respect to ID26, well, anyway, if we are not doing something, which has a spectroscopy or beamline, which has a user community, or which had a person who developed this code with a graphical user interface, when we have no options as to learn Python.
Yes.
Yeah, I agree. We do the same for the, if you really on quick exhaust, then you have to get into programming, because you get thousands of files, and but not so sure if you run so much quick subs in the future. If you do RIXS also you need, because also RIXS in Hamburg has this file format which you directly import. That's one of the points.
But luckily in Hamburg again there is a person who did a graphical user interface for that.
I think this will be the solution, that they have to do it for us, because if you go to many synchrotrons, you cannot write their own graphical user interface all the time, or they agree on the data format.
Yes.
Which I see difficult.
which is weird, because that's the easiest solution, and it requires the least, to some extent, least amount of work, because afterwards you need to develop tools which are able to convert, and like development of a graphical user interface to do calculations or like to do data processing is not easy. And even if you look at large, like this is XAFS view that Matt Newville is building, it's fine, it's fast, it has tons of features, but there are always can be little quirks and in the interface that are not how people want it to be used. And like people ask, why is it different from Athena? Like, why does it not look exactly the same? You know, I wanted to do it faster, but I wanted to have. So I understand that, and it's clear to me that the community, once you have your mind set on a way to do the data analysis, you do not necessarily want to change. So
it depends also on the level of let's say, of time people putting in. So maybe Dimitri works a whole day on EXAFS analysis. But usually our students are not doing only EXAFS. So they do in infrared, and they do another one, and they do some experiments, and they do some whatever. So maybe they work, I don't know, difficult to say, maybe 10%, 20% of their time. And then they would like to have a user interface. If you only data analysis on one beamline only, which have tons of data, for sure, then you're able to run these commands. But if you're going, we are going currently to 3 different synchrotrons, and maybe it comes up a 4th one now. And I don't know, the KID group goes even to more, I guess, than 4 synchrotrons. And I prefer to have a common program like Athena or Larkna, and they write converters for loading the data, rather than to have
to learn something new.
At every synchrotron to learn something new, exactly.
Okay.
It's already difficult enough to run the experiment. If you go to every synchrotron, every experiment is run differently, which is clear, because every beamline is built differently, but they are the people supporting you, helping you. So if you don't know the command, you can ask the beamline person.
Yes.
But if you then have to learn not only for every beamline and you write down what you did, then it changes continuously. So every time becoming every next new year, new options and new features. And then if you have also 5 different programs or 5 different packages for analyzing the data for the same data, of course, if you do RIXS and if you do quick exhaust and you do EXAFS and whatever, then of course you need a different program. But it would be nice to have one program like it was in Athena. So Dimitri, I guess, is not so long in the business, but I remember the time that I started writing my own EXAFS programs, I don't know, in the 90s without any graphical interface, and then there came one from Berlin, and then there came the one from, I don't know where was the other one from coming. But then since we got Athena, I think everything is quite straightforward. So there was Königsberger with his program, and there were so many people essentially, and you never knew if this what you're seeing is because of the particularity or the particular features in your program, or if this is really something. And now since we have this FEF calculation together with the Athena or LARC now, it seems that this discussion is that different programs give different results. It stopped, which was a really good point, because now EXAFS got much more, let's say, common use like it was in the beginning of 2000. So everybody had his own program, and really it was really like the case that you never know if this is simply the way you're treating your data, or this is really something new. There was this atomic XAFs and all these things happening. Now I think since we have a common program and everybody uses this program, at least everybody gets comparable data. I'm not sure if it's the best program, but at least everybody, there's not a discussion if my program does differently.
Yes.
It was really it limited very much the use of EXAFS. Because it was really magic. So it was, I do a Fourier transformation. What they're saying, well, it must be close to Einstein, no? Because you can do a Fourier transformation. And now things change, obviously. Now you click and it does it, like it is infrared spectroscopy. If you do infrared spectroscopy, nobody discusses how you transform your I don't know, your Fourier transform, how you get a spectra. Everybody says, I get a spectra, and then we discuss the spectra. And this is like an EXAFS now. Everybody agrees that we're doing it in the same way. And I think this was a big point on that everybody starts using the Athena or whatever programs you're going to call them.
Okay. So we have this discussion internally because and this is feedback that is actually extremely useful, because the idea is what to do next. Would we put effort in going and trying to develop something like, because Athena, they are going to go away at some point, unfortunately, because they are not being developed anymore. So what to put effort in what Matt Newville is doing and to build upon his large library, because large can also be used like I showed today.
I know.
But large as a library cannot do RIXS, cannot do X-ray emission. So,
but it can do a lot of quick stuff. So this is what we are doing. Then you can.
Exactly.
And the nice thing is you can do a one analysis and you get the output, and then you can copy it in and simply you get directly the Python script, and then you can directly or close to it directly Python script, and then you can use it. This is what we are doing for quick stuff, for instance.
Okay. Actually, this is very useful because it's
so essentially we analyze one set of spectra and then we look at the output, which is more or less Python, and then we say, okay, we have this parameter set, and then we just copy in the other file names and give it a go.
Okay, yes.
But ProgZAS is basically a user interface on top of large plus the model to import the quick EXAFS data. So.
Okay. But we're not doing so much quick EXAFS, you know. So we have I say we use it for not for quick EXAFS, but we use it if we really measure a lot of scans, but traditional scans.
Yeah.
Not if you have scans in the 50, 60, not thousands like in the EXAFS. So we're not doing so much EXAFS.
Actually, to confirm basically, Andreas, what you told, if you know what FastOsh is, so that's the software for PCA, MCR, ALS. Basically, that's again a graphical user interface developed by people from Soleil. And what they write in the description, like the first thing, a Athena-like interface. So it's based on completely different engine. It's MATLAB based, but with Athena interface, so that people are not scared of that. That actually works.
Well, we do the PCA still out of LARC, and we have there's a MATLAB interface for MCA ALS. This is what we are using.
So we basically implemented just the same MATLAB MCR ALS code, so that it's seamlessly, you import the spectra, you just click a button, you get directly this MATLAB input, and the output goes back.
When you say import, you're using like this type of file format that Athena used to export, like Athena project?
No, it imports, so the projects are not compatible. It imports in a similar way as Athena does from ASCII files, so you can set up which file you have.
Okay.
Which is the one? You developed it now, or what is this for MCA?
No, it's called Festosh. I would just type it in.
Okay. Because okay, we used the one which was FAB. Interessant. Everybody used it. See, this is a new thing now. It's again this ALS. This came up about 4 or 5 years ago, and now you see that again. Everybody develops different things, and in the end, one program will be the one we're going to use. Maybe this one. I don't know.
But under the hood, it's actually that one code which everybody still used even before it came. So it's just a convenient way to get your spectra in this code.
Good. Interesting.
Okay, sorry, I was told that we have to wrap up the session. Thank you for sticking to the end. I would be very interested, like, I mean, thank you already for giving me feedback on this. If you have any ideas that you want to share, I would be very happy to have them, because I really need this feedback from people that are more used to interacting with this type of software, to see what actually needs to be done. So I can transmit it also internally to see what we do as a policy for the ESRF, for example. Do we put effort in developing large, or do we do something that is... if you have any ideas, like short ideas, yeah, send me an email.
No, I really think again what we have discussed, I think for say reporting while you're there, I think this Jupyter is really very useful.
Okay, that's
because you can say I've done this, you can look at the data, you can do a little bit analysis. I think that's very useful. So simply for reporting while you're doing the experiment there, I see it very, very interesting.
Okay, sounds good. Okay, thank you, and have a nice afternoon, and enjoy the rest of the meeting.
Okay, bye-bye.
Bye-bye.